Hello everyone, let's try to be a cheat code ninja today. In this problem, we are given a binary tree and we have to return the largest values in each row of this tree. Let's understand this with the help of an example. In this binary tree, we have 3 rows. In the first row, we have only one node and the maximum value is 1. For the second row, we have 2 nodes and the maximum value will be 3. Similarly, for the last row, we have 3 nodes and the maximum amongst them is 9. Hence, the result array will be 1, 3 and 9. Please note that the result array should first contain the maximum value from the top row, then the second row and so on. Let's look at multiple ways we can solve this problem. The first thing that comes to our mind is that we have to do some kind of tree traversal. Hence, we can either do BFS traversal or a DFS traversal. Since we have to find the maximum value row-wise, it seems more intuitive to traverse the tree row-wise. Hence, it's easier to solve this problem using a BFS traversal. This problem can also be solved using a DFS traversal and we'll also look at that solution. As with all BFS traversals, we'll require a queue where we'll store all the elements row-wise. And for each row, we'll keep track of the maximum value that we have seen so far using a variable. We'll initialize this with -infinity. And after going through each row, we'll store the maximum value for that row in our result array. We'll start with the root node and add it to our queue. This will be the new maximum for this row. Hence, we'll set 1 to be the new maximum. It has 2 children, so we'll now add them to the queue. Now we have no more elements left in this row, so this will be the maximum for this row. Now we'll repeat the same process for the second row. We'll again initialize our maximum value to be -infinity. We'll start from the next value in the queue. This will become our new maximum. We'll now add its children to the queue. Now we'll move to the next node in the row. Its value is less than the maximum we have seen so far, so we'll not update our maximum. It has only one child and we'll add it to the queue. So the maximum for this row will be 3. We'll repeat this process for the next row and reset our maximum to -infinity. Our first value is 5 and this will be our new maximum. It doesn't have any children, so we'll not add anything to the queue. Our next node is 3 and this is not greater than the maximum that we have seen so far, so we'll not update our maximum. Our next value 9 is greater than the maximum that we have seen so far, so this will be the new maximum. We have no more values left in the row, so 9 will be the maximum for this row. Now there are no more elements left in this tree, hence this will be our answer. The time complexity of this would be O of n because we have to go through each element only once. And for the space complexity, we have to maintain a queue and that can take size up to O of n. Now let's take a look at the DFS solution. In this also, we'll keep a result list to store our output. While we do our DFS, we have to keep one thing in mind. Since we have to find the maximum for each level, we'll keep track of these levels by passing an extra parameter. These levels will correspond to the indices in our result array. Let's take a look at a complete example. We'll start with our root node and it will be at level 0. Since we don't have any value at index 0 in our result array, this means that this is the first value that we have seen for level 0. Hence we'll store its value in our result array. Now we'll call DFS on its children. We'll first go to the left side and this will be at level 1. Since this is the first value that we have seen for this level, we'll store it in our result at index 1. We'll now call DFS on its children. Similarly, this value 5 will be at level 2 and this will be the maximum that we have seen so far for level 2. Now we'll go to its right sibling. Since this value is lower than the value we have stored at index 2, we'll just ignore it. Now we'll go to the right child of our root element. This is lower than the value stored at index 1, hence we'll ignore it. And finally, our last value for level 2 is greater than the value stored at index 2, hence we'll store it over there. We are now done with our DFS and this is our answer. The time complexity of this will also be O of n because we are going through the elements only once, and the space complexity would be O of n because of our recursive call stack. Let's implement both our solutions. Let's first implement our BFS solution. We'll initialize a queue and add the root element to it. Let's initialize our result list. Now we'll go through all the elements of the queue till it is non-empty. We'll keep a variable to store the maximum value that we have seen so far for this row. We'll go through all the elements in our current row using a for loop. All the elements in the queue currently belong to the same row. Hence we are using the length of the queue. Our current node will be the left node in our queue, hence we'll pop it. We'll have to check that it is not null. This is because we'll not check while appending to the queue whether the left child or the right child is null or not. If our current value is greater than the maximum value that we have seen so far, we'll update it. Now we'll append both the left and the right child of this node. Since we are already checking if our current node is not null, we don't have to check if the child node exists or not. We are now done with the BFS for our current row. There's one corner case that we have to handle where our current row can be empty. In that case, the maximum value will still be minus infinity and we don't have to append that value in our result. If it is not minus infinity, we'll add this value to our result. Once we have no more elements left in the queue, we can return our result. We are now done with our BFS solution. Now let's implement our DFS solution. We'll initialize our output to be an empty list. Now we'll write our recursive DFS function where the first parameter will be our current node and the second parameter will be our current level. Our base condition for our recursive function will be that if our current node is null, we'll just return from the function. Now we'll check if the index level is present in our array. So if the length of the result array -1 is less than our current level, that means we have to add this to our result list. If our current level is already stored in the result list, in that case we'll compare its value to our current value and maximize the value at that index. Now we'll call DFS on the left and the right child, and the level for the children will be one more than our current level. We are now done with our DFS function. We'll call it on the root element and after that we'll return our result. Now we are also done with our DFS solution. If you have any doubts or concerns regarding this solution, please mention in the comments. If there's any other problem that you would like to see, please mention in the comments. If you thought this video was helpful, please leave a like and subscribe to the channel for more such content. Thanks for watching.